Okay, so maybe I should begin. Is it okay? You can hear me, everybody? Okay. So the purpose of today's tutorial is to give another approach to the homomorphism theorem that you've seen this morning. So first of all, why giving another proof of a theorem? Well, first of all, it increases the chance that the theorem is true. And secondly, well, you will see there will be a lot of nice pictures and nice notions that I'm going to introduce to give you the proof, the original proof of Jean-François Le Gall and Frédéric Paulin of this theorem of this morning. So, as usual, let me begin with a little summary to reintroduce the notations. Okay, so recall that we were dealing with planar maps, and you probably remember that if we take the contour function of the trees associated to the planar maps together with the label functions renormalized by the proper factor that you know by now, together with a distance that we define first on 0, 1, that this triple for ST between 0 and 1, well, this triple converge in distribution at least along a subsequence, nk, towards the Brownian snake, together with a distance here. Maybe I should renormalize as well. Okay, so let me first comment on this convergence. Well, as usual, by the Skárahod theorem, you can replace here the convergence in distribution by an almost sure convergence. Well, this is not a big deal. Maybe if you're not familiar with this, well, it's not just a magical trick. We can couple all the realization of these variables such that on some probability space, the convergence is almost sure. So this is not a big deal. Here is the big deal, the subsequence. Because for the first two components, the contour function and the label function, this we know that we have convergence towards the Brownian snake. But we need to extract for the third component to have convergence of this pseudo distance on 0, 1 towards a pseudo distance on 0, 1, dst. You've got two components here. And this really needs the extraction along a subsequence. Okay, so maybe I can begin with a remark. Well, the uniqueness of the Brownian map, roughly, is equivalent to the fact that we don't need to extract a subsequent such that the third component converges as well. So, uniqueness of the Brownian map. Well, maybe I should first define what the Brownian map is. So you've seen that the Brownian map, M, was defined as the quotient of 0, 1 by this pseudo distance, d0, and the metric space. So M endowed with this thing is now a distance on this set, is called the Brownian map. Okay. And so now the uniqueness of the Brownian map, open problem at this hour, maybe not in 2 hours, but at this hour, this problem is still open. It's equivalent to saying that we don't need to extract for the third component to converge. OK. Is this clear? It's the third time you're seeing this, so it has to be clear. So after that, in the last lecture of Jean-François Le Gall, you've seen that this space, the quotient of 0, 1, can actually be seen as a quotient of the tree coded by the excursion. So in fact, the distance d can be defined on TE, well, meaning that if S and T are in 0, 1 such that, well, they represent the same point in the tree, then the distance between these 2 points is 0. So we can define the distance on the quotient space of 0, 1 by this pseudo distance, which is exactly the Brownian tree. So the Brownian map is also expressed as the quotient of T by a strange pseudo distance and endowed with the pseudo distance which becomes a distance on this space. Okay. So after that, the real tour de force is to identify this equivalence relation. So, let me state the theorem. You've seen this morning, but let me remind you of that thing. So, almost surely, if A and B are 2 points in the CRT, then the distance between these 2 points, well, the distance defined on the tree is 0, if only if, well, A equals B, which is obvious, or A and B are leaves, and the label at A is equal to the label at B, which is equal to the maximum of the minimum along AB in the tree of Z and the minimum between BA in the tree of Z. Okay, let me introduce this notation. Okay, I introduce on a picture. You've got the Brownian CRT like this. Take A here and B here, 2 leaves. And so the segment, not the segment, but this part AB with a parenthesis on this is just the contour between A and B in clockwise order in the tree. So this is AB. And the other contour from B to A in clockwise order is BA. Okay. So this is a real tour de force. This is, well, maybe the deepest theorem we have on planar maps. So let me comment. Well, it's easy that if one of these properties is satisfied, then the distance is equal to 0. So this only comes from the continuous, yes? Sorry? Tour de force, it's a very difficult theorem. Tour de force in French, it's a, well, you're proud of yourself when you have proved that theorem. Tour de force. Here, you mean the contour? From the function? Well, I don't want to spend much time on this because we already saw this morning. Take S, a point such that the projection of S, a point in 0, 1, such that the projection of S is A, and T such that the projection is B. So this contour is just the projection of the segment ST in 0, 1. And this part is the projection of, well, T1 union 0S. But I prefer not to be very formal because you will see it's not formal after that. So just imagine that it's the contour of the tree in clockwise sense from A to B and from B to A. Okay? So you know that if, when you do this contour, you have no label which is strictly less than A, in the Schaeffer bijection, you will have an arc between this point and the first point, which is this one minus 1, which will be this one in the continuous. Okay, so this is, well, this implication is obvious. The other one took a lot of work. Okay, so now that we have this, well, you can consider the Brownian tree together with its distance, and you can consider the projection on the set M, the Brownian map, which was defined by this quotient together with the distance D. Just the projection, you consider a point on this space, you take its equivalence class in this. So I claim that this arrow is continuous. So this is continuous. So why is it continuous? Well, a priori, we don't know anything about D. Well, we do know a lot of things about D. For example, we know that D is less than D0. So let me remind you of D0. OK, because D is less than D0, and you will see that D0 is controlled in terms of this distance. So D0 between A and B. So I only define for leaves, but it is easily defined. So it's ZA plus ZB minus twice the maximum of the minimum between the contour from A to B in clockwise order of Z and the minimum in between the contour from B to A in the tree. Okay, so this bound came from the analogous upper bound in the Schaeffer bijection. Okay, so here you see that if you move a little bit the point A, then Z will move a little bit because it's continuous. The same here. So this is continuous for DE. And since we have this bound, this projection is indeed continuous. I mean that if you move a little bit the point in the tree, it won't move by a big amount in the Brownian map. OK? So I only say that to introduce this commutative diagram. Don't be afraid. So you've got the projection onto TE quotiented by D equals 0 endowed with the distance D. So you know that this arrow can be factorized by the equivalence relation DAB equals 0. Maybe I also introduce, if A and B satisfies this, I denote this by A tilde B, as in Jean-François Le Gal's lecture. So you know that this can be factorized by this equivalence relation, or if you prefer, this is the equivalence relation defined by D equals 0. But here I put the quotient topology, and here you've got the factorization of this projection. OK, this, don't be afraid, I will do a reminder on quotient topology in 5 minutes, but this roughly says that if you have a map, continuous map, which is constant on any equivalence class of a given equivalence relation, then this continuous map can be factorized through the quotient space endowed with the quotient topology, and you've got a continuous arrow here. So continuous. Okay? So you see the difference here. The two spaces, this one and this one, they are the same. Well, the points are the same, but the topology is not the same, a priori. Because here you've got the topology defined by a distance, and here you've got the quotient topology. Okay? So what I claim is that this thing, which is the Brownian map is a metric space. You've got a distance. This thing is compact. What I claim is that this thing is compact as well. You will see in a minute, 5 minutes. No, this is second, 5 minutes. So, and this projection, now that we took the quotient, and since we have this very nice theorem due to Le Gall, maybe Le Gall, 07. So you are now enabled to say that this equivalence relation, which was a priori defined only in terms of the tree and the Brownian snake, this, well, you see this equivalence relation is defined in terms of Z. And, well, the theorem says that this equivalence relation is indeed the equivalence relation defined by this pseudo-distance. So these two sets are the same, so this is a bijection. Well, now I have a continuous bijection between two compact sets, so it's an homeomorphism. All this to say that, well, we don't know D, but thanks to this theorem, the topology of this space is exactly the topology of this space with the quotient topology. Okay? So I've been asked the question why this theorem characterizes the topology of the limit. Well, now you see why. Okay, so the goal of this lecture is to identify now this topology, which is only defined in terms of E and Z. You've got no D inside this statement, no D, because the equivalence relation til-til was defined in terms of the Brownian snake. Yes? Yes. On the subsequence, exactly, because D depends on the subsequence, depends on NK, but whatever the subsequence you're taking, if you have convergence, then, well, you don't know D. D might depend on the subsequence, but D AB equals 0 is totally characterized by this. So we don't know D, but we know when 2 points are identified by D. So if I give you 2 points, you cannot say if these 2 points are in distance 3, 2, or 4, but you can say if they are at distance 0. That's exactly what this theorem is telling you.
So as homological spaces, only subsequential limits are the same.
Exactly, because you see here, this space might depend on NK, but in this space, the equivalence relation til-til is not defined in terms of the NK. It's defined in terms of A, B leaves, Z, and E. So you don't have any subsequence because you know that in the convergence on the first blackboard, the first two components, they converge without taking a subsequence. Okay?
So the lack of uniqueness is only because we cannot say for sure that the metrics are the same.
Yeah, exactly. It's the first remark. Okay? Clear? Okay. So let me make a crash course on quotient topology. So you see the point. Now we have, well, maybe during my wipening of the blackboard, I should say that, well, you can identify the topology, but nobody is telling you that this topology is almost surely the same. This is random. So the topology might be random as well. We will see that, well, you already know that it's not the case. So reminder, quotient topology. no, in red. So you've got a set X and an equivalence relation. Well, okay, no. I should speed up, so nothing to say. Okay, equivalence relation. So you've got a topology on X, topology. And, okay, so you can consider the set X quotiented by this equivalence relation is the quotient set. You define the pi, the canonical projection from X to its quotient set. And we want to give to this quotient set a topology. So the quotient topology is by definition a set O included in this quotient set is open for the quotient topology. So the quotient topology that I denote TQ, if only if you take its reciprocal image. So this set in X is open. Okay, definition. This is definition. And you've got the universal property that totally characterizes this quotient topology, and which is, well, why we introduced this topology. So universal property. So if you've got X with its topology, an arrow F which is continuous towards another topological space, we'll say M. And if F is constant on the classes of the equivalence relation, then this arrow F can be factorized through the quotient space with the quotient topology on another arrow that I call F bar, which is still continuous. So F can be factorized. Into F bar composed with the projection, canonical projection. Okay, so I guess this is clear for everybody. If it's not, raise your hand now and go out. Because I have no time to discuss this. Maybe you can come after the tutorial. Okay, so why is it, well, you see it's nice because of this universal property, but the quotient topology can be nasty. So for example, counterexample can be nasty. So take, for example, the interval 0, 1 with usual topology. Okay, and define an equivalence relation on this set by, well, X is equivalent to Y if only if X equals Y, or X and Y are positive. That means that I have two equivalence classes, the one which consists of the singleton 0 and the one which consists of all the other. Okay? Is this clear? So what is the quotient set? So this is X. These are my classes. Okay, so now if I take the quotient, well, I have 2 points in my quotient space, the point corresponding to 0 and the point corresponding to the others. And now what is the topology on this space? Well, it's easy to see that the topology, well, you have the open set that contains everything, and you've got another open set which contains only the second point. This point is not, this set is not an open, because if I take the reciprocal image, it gives me 0, which is not open, an open set. So this is not, the singleton, this point is not an open set. So you see that the topology is nasty. Why? Because the topology is not Hausdorff separated. Not Hausdorff. Not Hausdorff separated. Okay, and why? Well, it's very important for this thing to say that if you have a continuous bijection between two compact sets, to say that it's an homomorphism, well, you need that your compact are Hausdorff. So we need to exclude this phenomenon. Okay, and so we have a good proposition to exclude this phenomenon, which is the following. So proposition, if XD is a compact metric space, and tilde is an equivalence, closed equivalence relation on X, meaning that is closed mean, well, you take the set of points in the product of the space which are identified. This set is closed. Okay? So if you've got a compact metric space and a closed equivalence relation, then the quotient space with the quotient topology is Hausdorff, so separated, and thus compact, because this one is compact. You've got a canonical projection from a compact set, well, and compact, because the image of a the image of a compact separated guy by a continuous mapping is compact if the thing is separated. Okay, Hausdorff and compact. So I won't prove this theorem, it's just topology, but this theorem, this proposition, but here we will only deal with closed equivalence relation. So if in what will follow, if I forget to put closed equivalence relation, then you put closed. Is this so boring? I'm sorry, but okay. So in the following, in the sequel, all equivalence relation will be closed. Don't worry, I will be like Vincent when it's interesting. I just clap. Okay. So we want, what's the goal now? We want to identify this topology. So in order to check that this topology is the same as this one, I claim that this guy was compact. You just have to check that the equivalence relation tilde that I just erased, this one, is a closed equivalence relation. So this guy is compact, and you have a continuous bijection, so it's a homomorphism. Okay. So it's going to be interesting. So, okay, 1, 2, 3. Now, you won't see the link immediately, but I have to start by introducing what we call the Brownian lamination. I checked that I forgot nothing. Perfect. Okay. So the goal is to identify this guy. And to identify this guy, I will first try to have a nice description in terms of topology of the Brownian tree. So we take our friend, the Brownian excursion, we take E, and we see this process, E, as index. We see E as a process indexed by S1, the closed unit circle. So, well, it's easy. You just put this definition. You can see your Brownian excursion as running over the closed unit circle. Okay? And so I introduce if x and y are in the circle, then I introduce the closed arc from x to y in clockwise order, which is, well, this guy. X is here, y is here, and, well, yx is this guy. It's coherent with the notation I introduced at the beginning of the talk. So this is xy, this is yx, okay? And I define a metric, a pseudometric, dE of xy, which is, as you might expect, E of x plus E of y minus 2 times the maximum of the minimum between x and y of E and the minimum between yx of E. So you may say, well, I know this metric, but well, what is this maximum? What is the maximum of 2 minimum? Well, you see that if 0 is here, since the Brownian excursion is 0 at 0, then if I take x, y in this order, then in this maximum, well, the minimum over yx of E is 0. So this term will vanish. And you can recover the usual distance that you are familiar with. OK? And I also introduce an equivalence relation in terms of this distance. So for example, if you take the quotient of S1 with this pseudo distance and you endow this quotient by the pseudo distance, you are recovering the CRT. It's exactly the same. But here I put x is equivalent by E to y if only if dE of xy is equal to 0. OK. So nothing new so far. But now I define definition. The Brownian, the lamination, coded. So why lamination? It's a well-known object in geometry called lamination, coded by E, is by definition the random subset LE, which is the union over all xy running over S1, such that x and y are identified via E of the chord. I call this a chord xy. This is a chord. And this is just the Euclidean segment in R2. OK? So this is the definition. Let me draw a picture of this. So imagine you take your Brownian excursion, this, like this. OK? And you are given the circle. 0 is here. Well, 0 it's maybe here because 0 is identified to 1, but I want to put 0. Just. OK? And well, let me put 0 here so that I imagine that the excursion is running in that direction. So take these 2 points, this one and this one. They are identified via the excursion. Okay? Their distance is 0. So these 2 points maybe corresponds to this one and this one. So I should put an arc, a chord between these 2 points. Okay? Well, we've got other points. This one is identified, maybe another color. This one is identified with this one. And this one is also identified with this one. So you've got 3 points that are identified. And this roughly corresponds to something like this. OK? And you can go on. For example, here you've got 2 points identified. So this is roughly this. OK? And you go on. So you do this for all points that are identified via the excursion. This is LE. So proposition. Proposition. Almost surely, the random set LE is such that, well, any chord, any two chords, any two different chords of LE. So a chord is just a straight segment belonging to this union. So any two chords of E don't intersect inside D, in the interior, in the open unit disk. And, well, D bar minus LE is composed of Euclidean open triangles. Proposition. Okay. So, well, on this picture, you can see that, well, you can check that the chords I've drawn, they are, if they are different, they cannot intersect inside D. Well, this one don't intersect the blue ones or the orange one, but two chords can intersect on the boundary, these two chords, these two blue chords. Okay? And, well, here I've not drawn all the chords, so you cannot check that the complementary of LE is composed of open triangles. So maybe it's time to take your exercise sheet and to have a look at the back of the exercise sheet. And there is 3 pictures. And the second one is actually a picture of this thing. Second one? C'est bien la deuxième? Yeah, the second one. So you can check on the picture that actually it looks like described in the proposition. So let's do a quick proof of that. So what do we want to exclude? We want to exclude the fact that, well, here is 0. Here is maybe x, y, and w, and z. And you want to exclude the fact that here you've got a chord, and here you've got another chord. You want to exclude. Well, so imagine if it is the case. Here is your 0, and the Brownian excursion is running, is indexed by this circle. So if it is the case, then what would happen for the Brownian excursion? So you take, well, the point corresponding to x, this one, and the point corresponding to y, this one. So you know that they are identified. They are identified via the Brownian excursion. So that means that the Brownian excursion has a value at x and a value at y that is the same, and that the Brownian excursion is over x and y over the E of x, which is equal to E of y, between x and y. Okay, so you get a picture like this. And you know that at time w, here, well, you know you are forced by this picture to have a time z at which the excursion must have the same value here. And such that between time w and z, the execution is over this line. Well, think a little bit. The only possibility is that at time w and at time z, this execution has the same value as the value at x, y, and z. So this is exclude. This is impossible. Why? Yeah, that's what we did yesterday. Because here you can see that the Brownian execution has two local minima which are equal. And this is excluded. It's impossible. So this picture cannot happen. OK. And, well, you can check. This is exactly the same argument that is giving you the fact that all the things that you will have in the complementary, they are triangles. Well, maybe I can sketch the picture. Whoa, I must speed up. I've done 10% of the TA. So imagine that you have a picture like this. Well, what this would correspond to, well, you've got time A, B, C, and D. Well, you should have this at time A, B, well, A is here, B, C, and D. Here, maybe another color. It's exactly the same argument. So I only sketch. Here you've got this, this, and this. And furthermore, you know that if you have a square like this, then these lines must as well be part of the lamination because these 2 points are as well identified by the Brownian execution, and these 2 points also. OK? So this ends this proposition. OK, so now that I know what is the rough picture of the Brownian lamination, well, we know a lot of things about the Brownian lamination. For example, the Hausdorff dimension of this thing is 3/2. We know a lot of things because we know a lot of things about the Brownian motion. OK, so now I want to extend this equivalence relation. And I will extend, it will be clearer in the sequel, but I will extend this equivalence relation on the disk. So we extend this on D bar by setting, well, so x is equivalent to y by e in the disk if, only if, x and y are in some chord of LE. If they belong to some chord of LE, they are identified. Or if x and y belong to the closure of some component of D bar minus LE. Okay? So for example, I have things like that. Well, if x and y here are identified, if x and y are like this, they are identified. But if x and y are like this, they are also identified. Okay? So you imagine that somehow I shrink all the triangles that I get in my picture. Okay. So why did I do all these things? Because of the following proposition. Well, now you take the quotient space. So you take D bar with this equivalence relation that we've just extended, together with the quotient topology inherited from this equivalence relation. So this is homeomorphic to, well, the Brownian CRT coded by DE. You may say, well, it's very complicated to have something which is homomorphic to something that we know very well, but you will see that it's more convenient for what's going to happen. Okay, so why is that the case? So it's just a commutative diagram like this. I need just one line. I need one line. So you consider S1. S1, you've got the continuous inclusion in D bar, and D bar is projected by pi over D bar quotiented by this equivalence relation with the quotient topology. And you know that, well, this descends to the quotient. That I mean that if 2 points in S1 are identified by DE, they will be identified here. So this map can be factorized this way. And it's easy to see that this is a bijection, in fact, a continuous bijection. And since these two sets are compact, this is an homomorphism. So this is not complicated. It's just, imagine that S1 is 0, 1. It's just the 0, 1 quotiented by the equivalence relation, the pseudo distance, if you want, that will give rise to the Brownian tree. But on the other side, you can inject S1 into the Brownian tree just by projecting. You take a point, you take its image in the Brownian tree, and as well, this arrow can be factorized by the equivalence relation. Okay? And this is still a bijection. Well, all this space, this one, and this one, the set of points is the same. But I'm just dealing with the topology. So this is a continuous bijection. And since these two compact sets are compact, so this is also an homomorphism. So this one and this one are homomorphic. Well, you may say, no, it's complicated. But no, not at all. Not at all, not at all, not at all. Well, because imagine, well, this is hand waving, but I'm here for that. Imagine that you have your tree like this, your lamination like this. And imagine that you contract, that's exactly what is doing the equivalence relation. It's contracting, all the points here are identified. All the points here are identified. All the points here are identified. So imagine you do that. What do you end with? Well, shluk, shluk, shluk. You will end with something, this is only a point linked to this component. This point will be linked to this component, as well as here to this component. So you see that you get the tree structure, and that somehow, but this is not only a drawing, somehow the Brownian lamination, this thing is the dual of my Brownian CRT. And this is exactly what's happening. So we take the dual, and then we contract the dual, which is the same as taking the dual again, and we end up with the Brownian tree, but we've lost the distance. But this is still homomorphic. Okay. Okay, sorry for going so fast, but I want to get to the point. Okay, is it rather clear what I'm doing? Okay. So now, same idea with the process Z. So I claim, and you will admit that the process Z, which is the head of the Brownian snake that has been introduced in the very first lectures. So the process Z has distinct local minima. Okay? So it's, if you want to see this, it's a process over 0, 1, something like this, that ends at 0, at 1, which is not positive. But this process has local minima. And I claim that I can define exactly the same thing as what I erased. Well, you remember it was, well, I can define the distance dz between 2 points on the circle. I see as well the process z as indexed by the circle, and I can define the distance dz. And this, in the very same way as we just did, give rise to another equivalence relation that I denote tilde z, but to be very clear, I put double tilde. Okay? So this equivalence relation, if you want, this process will give me another lamination, which has only triangles, like this, only triangles, and well, things like that. And I can associate on this disk an equivalence relation defined in the very same way, and well, but I don't take the quotient directly. Okay? This is. So by the way, since this process is not positive between 0 and 1, you can reach 0 and reach negative values. That's exactly why I introduced this max of mean between the, well. Okay. So now we are coming to the nice pictures. So I need some room. So we did all this just in order to do these two pictures, the Brownian lamination and the lamination coded by the process Z on the same picture. So how can we do that? So it's an idea due to, first I guess, to Thurston. Okay, so you imagine that you, so let's see if it's working. Not too bad. So you take the sphere, that's the first time the two-dimensional sphere is appearing. Well, not so nice. Okay, this is the two-dimensional sphere. And I can see the north hemisphere. I can identify this as a disk, right? Same process on the south hemisphere. I can identify the south hemisphere to a disk. Okay? And I can see the equator as my S1 circle. So let's say 0 is here, and I'm running from 0 to 1. I come back here. Okay? 1/2 is here. Okay? And now I imagine that on the north hemisphere, I'm dealing with the process E. And on the south hemisphere, I'm dealing with the process Z. And I do exactly the same procedure, same device as I did. I mean, if 2 points on the circle are identified via E, I put an arc. So let's see. So I will draw arcs with fancy geometry, but imagine that it is straight lines or hyperbolic lines, if you want. So 2 points here are identified, so x and y, and they are identified via the equivalence relation defined in terms of E. So I may have 3 points like this, which are identified in terms of E as well. So I can have something like this. Okay? And my equivalence relation tilde E will imagine that we contract all these triangles and all these arcs. It's still written on the board. And I can do exactly, I claim that I can do exactly the same thing on the south pole. That is, if 2 points are identified via Z, I just put arcs like this. Okay? And the process, the equivalence relation tilde, double tilde z will identify these triangles. Okay? Okay. So now I define, okay, 10 minutes. If you give me 5 more minutes after the hour, maybe I can do the job. If not, then you can go. Okay, now we will extend this equivalence relation that we defined on the North Pole and on the South Pole. So here is Brazil, here is France. Okay, so we define the equivalence relation something as follows. So it's just the concatenation of the two equivalence relations. So x is equivalent to y if only if x is equivalent by e to y. So that means that x and y belongs to the north hemisphere. Or x and y are identified via the process z. That means that x and y belong to the south hemisphere. Okay? So just imagine this point is identified with this point. This point 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 with this one with this one, etc. Okay? But proposition, this thing is an equivalence relation. I put closed, but I swipe this under the carpet, is a closed equivalence relation. Well, you may say, why is it a proposition? Well, it's not trivial at all. Imagine that we can have the following picture. We have 2 points which are identified via E, and this point is identified via Z. So let's take, for example, x here, y here, and little z here. So x is identified to y, and y identified to z, but it's not clear at all. Well, it's not true that z is identified with x. So it's not an equivalence relation in general. But here it's the case. Why? Because we have this proposition of this morning. Maybe I can... Well, I won't state the proposition. It's in your notes. I have to gain time. But, well, if this picture is happening, that means that here, okay, I take... Look, I'm drawing the same picture. This arc means that here the excursion, the Brownian excursion running that way, the Brownian excursion is strictly bigger of these two values between these two times. So you've got the Brownian excursion here between these two times. Here the Brownian excursion is something like this. Okay? It's strictly bigger than this value and this value. Okay? Because they are identified. And similarly, with the blue color, if this point is identified with this point via the process Z, that means that the process Z, well, has the same property. I mean, this point, the process Z is takes bigger values here between these 2 points. Okay, but here you see that you have an increase point for the Brownian excursion and another increase point for the process Z. So this point is a double, I'm sorry, I'm going quickly, I know, but double increase point for E and Z. And this cannot be true because of the proposition star of this morning. Star of this morning. tells you exactly that this picture cannot happen. So if this picture cannot happen, that means that if a point on the equator, is identified via E to another point, then it cannot be identified to another point via Z. Okay? So let me write this. Okay, let me write this. If x in the equator, because it's the key point, if x in the equator is identified to y in the equator via E, then x cannot be identified to another point via Z. Okay, so this is an equivalence relation, because if this point is identified to this point, then if you've got another guy, then the other guy must be in the north hemisphere. So this is an equivalence relation. Whew. And now we've got the following theorem. So you see the nice picture. The nice picture, this phenomenon cannot happen. This phenomenon. This is impossible. Okay? Two arcs glued at one point. Impossible. The feet of the arcs of the cord, they are alone. That's exactly what this thing is telling you. Now we've got Moore theorem. Due to Moore, which was not a very nice guy, but nevertheless, Moore is telling you that if this is an closed equivalence, well, I'm running over time. Would you excuse me if I take 5 more minutes? Because if I stop here, it's not clear. So if this is an equivalence relation such that the classes, when I reach this part of the board, I stop. But I will erase such that the classes of this are closed path-connected set whose complement is connected, then the quotient S2 is a close equivalence relation, on S2. Then the quotient space is homeomorphic. Quotient space with the quotient topology is homeomorphic to the two-dimensional sphere. So let me comment on this theorem. I draw 2 pictures. So imagine that we take the sphere and we define an equivalence relation. All the points are identified with only themselves, except all this part. I identified all the points in this part, but 2 other points are not identified. It's defining an equivalence relation. You can easily check that this equivalence relation is closed, and, well, the classes, this is a class for my equivalence relation. It's path connected, and such that the complement is connected as well. Same for this one. Now imagine that we take the quotient of the sphere via this relation, this equivalence relation. What do we get? Well, we end up with the sphere. Well, this little thing just has been contracted. So it's still a sphere. Okay? But now imagine the picture where we take the sphere. All the points are identified with only themselves, except this part, which is totally identified, and inside the points are not identified with other points. So this defines an equivalence relation. And if I take the quotient, then all this part, all this annulus will be, you see, pinched, and we end up with two spheres glued together via this point which has been identified. But this exactly is the phenomenon that is provided in this theorem, because take this equivalence class for the equivalence relation. This set is path connected, no problem, but the complement, which is this, is not connected. So the quotient is not the sphere. Okay? Now, look at my nice equivalence relation. Look at the picture. Do you see any equivalence class which is not path connected, whose complement is not connected? Well, no, because exactly when a point is connected to another point, then they have to be alone. Because, well, if you would contradict the Moore theorem, you would need something like this. Well, it's a very simplest picture, but nevertheless, you would need something like this. This is identified, and, well, for example, something like this. This is identified, and since I glued my two equivalence relations, this thing becomes a set which is totally identified. But this does not happen in my picture. So the equivalence relation I've just defined satisfies the assumptions of Moore theorem. Okay? So now, I've got my two sphere. I quotient with my equivalence relation. This is still homeomorphic to the two sphere. But imagine now, what can we imagine? First, we imagine that we contract the North Pole. If we contract all this pink thing, the North Pole will just become the CRT up to homeomorphism, because it's exactly the disk that we quotiented via the equivalence relation defined in terms of D. So if we quotient the North Pole, we end up with the tree, the Brownian tree. And what's remaining is just the identification in the theorem of Jean-François Le Gall. The identification if two points are identified by Z. So it's not difficult, and I leave it as an exercise because I'm 10 minutes late. This thing is equal to, well, this. First, you quotient by the equivalence relation defined in terms of E, and then you quotient with this equivalence relation, and this thing is exactly the Brownian tree quotiented by the equivalence relation double tilde that I introduced at the beginning of the session with the quotient topology. So we wanted exactly to identify the topology of this thing. And we have, to sum up, we have written this space with the quotient topology as the quotient of the two sphere with an equivalence relation. What was the trick? The trick was to take the two hemispheres. The north hemisphere is coding the tree. The second hemisphere is coding the equivalence relation, the tilde. If you want, these are the arcs of Schaeffer bijection, if you want, in the continuous. And then we contract here, we got the tree. We contract here, we get the Schaeffer bijection. We just use this very nice theorem that if you don't have this phenomenon, then what you get at the limit with the quotient topology is a sphere. And that's giving another proof, well, the first one in the history, that the scaling limit of the random planar maps are almost surely homomorphic to the two-dimensional sphere. Thank you. Are there any questions? You want me to recap? I'm sorry, very sorry for being